In this video, I will be talking about spin-orbit coupling. And so we need a correction to the energy for spin-orbit coupling, as well as the fine structure of hydrogen, which was the last video. And at the end of this video, I will combine those two together to show the first order correction using both of these. And so from the electron's point of view, the nucleus is actually orbiting the electron. So, that's kind of that relativity thing that's, that's why it looks like the sun is orbiting the Earth. But this means that there is a positive current moving around the electron. And we would know from electrodynamics that a positive a current of any kind will produce a magnetic field. And so because the electron also has spin, it also has a dipole moment. And so the magnetic field generated by the proton in a hydrogen atom will actually exert a torque on the electron. And by the way, this analysis can be done using the electric field if we want to look at it from the proton's point of view, quote unquote, but the math is a bit more involved and ends up getting you the same thing anyway. And so it's done like this using the magnetic field, thinking of the proton as orbiting the electron. So we need to find out then what the magnetic field B and the magnetic dipole of the electron mu are. So the proton, which we can model as a sort of continuous current loop, so it's like a loop of current going on around the electron, has a magnetic field given by this law. I'm not even going to try to pronounce it. So we have the B equals mu naught I over 2R, where the effective current I is equal to the positive charge over the period of the orbit. So charge per time, which is what current is. So the angular momentum of the electron from the point of view of the nucleus is this 2 pi mr squared over t. And so if we do some rearranging, so we have our magnetic field here, we put in the E over t for the current, and then for this one we have the L, which is the angular momentum, equals 2 pi mr squared over t. We just switch the L and t around. So we just multiply both sides by t, divide both sides by L. And so then we can put this right here in for the t on the magnetic field. And so we end up getting the magnetic field equaling this. And so then Griffiths does this, the c squared is equal to 1 over this epsilon naught, mu naught, which are the permeability and permittivity of free space. And so this is so we can get things in terms of this epsilon naught rather than the mu naught, which will give us our electrostatic potential formula. So this is our magnetic field here. So this B is equal to this 1 over 4 pi epsilon naught. Then we have this E over mc squared r cubed, and then times this L operator right here, this angular momentum operator right here. And then so we want to find out what the magnetic dipole moment of the electron is. In the current is this q over t time. So the magnetic dipole is the current q over t times the area pi r squared of the ring around which the charge is sort of smeared out. And so that gives us the q pi r squared over t. So the mass of the ring is m, its angular momentum of inertia is mr squared, so multiplied by the 2 pi over t. So this gives us the s equals 2 pi mr squared over t. And so the gyromagnetic ratio is, so if we put these two, if we divide each of these by each other, we get this q over 2m here. So our mu over s. So the the magnetic dipole over the angular momentum. But this is for classical electrodynamics. For the gyromagnetic ratio is actually this mu over S equals G Q over 2M, where G is the so-called anomalous magnetic moment, and that's our G equals 2. So you may have heard of like this G minus 2 factor or whatever, and it's this thing that physicists are very proud of themselves for being able to measure to such a high degree of accuracy, because it's actually not exactly 2. It's 2 point, I think 002 something something something. But anyway, you can look that up. But we will just think about it as being essentially 2 for now. So we have our mu over s is equal to this 2 over, or 2 times q over 2m. So it's just q over m. So if we multiply both sides by s, then our dipole is this mu equals, and I put the E plus here because we're now thinking of the positive charge of our proton, divided by mass times our S operator here, so our angular momentum of the electron operator here. And so we therefore have the following. So we have this for our B, our magnetic field, and then this mu for our magnetic dipole. So we want to multiply those, or take the dot product of them, and we put the minus sign there. So we put this together, and then when we well, we have this L and we have this S here, so we have this as our energy, the L dot S there. So this is the electrostatic potential here. We have the 1 over m squared c squared r to the third power here. But we know that this can't be right because the proton or the electron, if we're thinking of the proton's point of view, are actually orbiting, which means there's an acceleration going on. There's an acceleration inward towards the nucleus of the electron. So in special relativity, we'd say that the orbiting particle is undergoing a constant series of Lorentz transformations. So it's sort of boosting into a new inertial frame of reference at pretty much every point along the orbit. And this is actually called Thomas precession, which I'm not going to get into too much here. What this amounts to for us is that it actually subtracts 1 off the G factor, which we had as 2. It's not exactly 2, but we've been calling it 2 for this. So it ends up being G equals 1, which essentially just puts that 1/2 back into it. And so we just put this 1/2 here, so this 4 becomes an 8 right here. So essentially what this is saying, so this, as I said, is the Hamiltonian here for our spin orbital coupling. And so what this is saying is that the magnetic field caused by the proton induces a torque on the electron due to the electron's spin. But what does this mean, though? It means that the Hamiltonian doesn't commute with L and S. It does, however, commute with the L squared, the S squared, and the sum of the L and S, which will give us this new operator here. And so its z component and its square will also commute with the Hamiltonian. This j squared is the L plus S times L plus S, so we just FOIL that out. We get the L squared plus S squared plus 2L dot S. And so then if we just sort of solve for the L dot S, we get the L dot S equals 1/2 times J squared minus L squared minus S squared. But recall that the eigenvalues of L squared and S squared are these H bar squared L times L plus 1, this H bar squared S times S plus 1. So the eigenvalues of the L dot S are this right here. So we have the J squared, and we're taking the eigenvalue of that, which is J plus 1. Then we're subtracting the eigenvalue of the L squared and the S squared there. And we know that the S is going to be a spin of 1/2. And so we have the S times S plus 1 being equal to this 3/4. So we can do the expectation value of this 1 over r cubed, which in this one I haven't actually put the math for this at the end like I did for the 1 over r and 1 over r squared last time. But the process is very similar, and we just get this 1 over L times L plus half times L plus 1 times n cube a cube. And so the first order correction for the energy of the spin-orbit coupling, this ESO here, is going to be equal to this large thing right here. And so we use the Bohr formula and Bohr radius here, and so we can put those in, and we do a bunch of sort of algebraic manipulation, and we get this right here for our spin-orbit coupling energy. And so then if we add this to if we add the fine structure energy correction here from the previous video, so we are adding these to get our sort of EFS here. So we take this one that we just found here, and then we add, well, this negative one here, so it's subtracting. And so if you go through a bunch of math and a bunch of algebraic manipulations and substitutions and things like that, we end up with this right here. So we combine that with the Bohr formula, and so we end up with this down here. So we get this minus 13.6 electron volts from the Bohr formula, this n squared from the Bohr formula. But now the thing to see here is we have the alpha squared, which is our fine structure constant. That's that 1 over 137. Then we have this part here, which is the correction from our spin-orbit coupling. And so this is the energy correction right here. Well, the minus 13.6 electron volts over n squared is the energy from the Bohr formula. Then this stuff here in the square bracket is the correction for the spin-orbit coupling and for the fine structure of hydrogen, or at least the first order correction anyway. But anyway, that is everything I wanted to talk about in this video. I hope you found this interesting, and I will see you in the next one.